Is it possible to understand me in the back of the room? Okay, good. So, welcome back. I'm glad you all found it. We started a little bit later this time because apparently the room was booked until 4 o'clock for these people before us, but it's all set up now. I'm going to talk about informed search today. So that's the sort of second method for dealing with these state spaces in order to find the right decision. Before I want to do that, I have a couple of things I want to talk about. First one is that there is a course, Intelligent Systems, also in period 3. And maybe some of you might have by accident also registered for that, but it's a different course and it's for second year students. So if you're also registered for a course, Intelligent Systems, in the third period in January, then you should deregister again, because you can only follow one of those courses. Then the second thing is that there was a midterm scheduled, I think, on 22nd of November, but that was by mistake, so that wasn't intentional, and I removed this from the schedule. I believe it should have been gone now. So also to make very clear, so that there will not be a midterm. And then I wanted very briefly to ask you whether you have any feedback on the working groups on last Thursday, Friday, on the computer practicals, and maybe also on the lectures, on the videos. Is there anything we should change or do differently or improve? So you can always send me an email, but now it might also be a moment to let me know if there is anything, and we can check whether that's something that's shared by more of you. So if you have suggestions, yeah.
Specialized, or we had the knowledge of the topic we were discussing. So eventually, all of us arrived in the room and we had to work by ourselves in silence.
Yeah.
And then we had like 15 minutes to discuss everything. So, and everything was like done in 15 minutes, very fast. So eventually we had questions. You still have them eventually.
Okay, so is it something that is, so in principle, I usually leave the way of running these working groups to the TAs. And one way is that you go to the TA and say, would you mind doing question by question, so that we can then discuss the questions and have more time for feedback. I can also give that as feedback. So what is what do the other people think in the room? Was that, is it a recognizable problem, or was it just this one working group? Yeah? Okay. So I think it depended on the group, and so I would suggest that we discuss this with the TA, and so that next time he does it in a more efficient way or effective way for you. Yeah. Do you want me to take that up with the TA, or do you want to do that next time? Yeah, if you see him. I mean, otherwise, let me know who it is. Send me a quick email, and then I'll talk to him briefly. So did anybody look at the videos of the lectures? Is that worth doing it? Yeah, because it is quite some work to collect that, to record them, and then to transform them and put up. And I only want to do that if you really consider that as something useful. But I see many people nodding, so I guess that's worth it. So I want to have one final word on the practical assignment. And so I think you're looking at programming from two completely different perspectives in the last week. So the one is the very systematic lessons that you get from Matti, where you really learn the individual concepts and the way you write them down. You really learn how to program in a systematic way. And the other way is that you start from, there is a program, get going, try to sort it out from a program level. And both of them are very important parts of dealing with programs. And so I had some contact with the TAs, and they said that in principle at the end of the sessions, everybody who was there was more or less able to play around with the game engine and play around with the programs a little bit, so that you got over the first threshold. Is that a correct assessment? Or are there people who say, I have no bloody idea what I should do and what this program, how this works and so forth? If that applies to you, now would be a good moment to shout. I heard a tiny little shout here somewhere. Okay. So you don't need to shout in public. You can also come to me after the lecture, or if that is less embarrassing for you. But please let me know, because otherwise we can't change anything. So let me go to the point of what's called informed search. And remember last time that we came up with a generic representation of problems in state spaces, like the filling up the jugs, and then you had a certain action, and this certain action would bring you from one state to another. So in the state, the left jar had 2 liters and the right hand had 3, and after some action, the left hand was empty, or some other action brought us to the state where the right was empty. So these were really sort of abstractions over situations in the real world. So these are the states. And now we have some of these states, which are the goal states. And the question is, how can we, from the initial state where we are in, get to one of the goal states at the end in an algorithmic way? And that is what these search algorithms do for us. And in principle, the most simple algorithms we looked at last week were just systematically going through all the options that you had by building a search tree. That was all we did last time, and how we did that was to put the initial state in our fringe, which is just some data structure, and then in each of the loops, you take the first element out of this fringe. You see what are the options, what are the children in the search tree, what are the options that you could get to with a certain action, and then put those new options that you could derive with an action back into your data structure. And that could either be a queue or a stack, a FIFO or LIFO, but in principle, these nodes were unordered. And there was no real logic why we started with a certain node first to explore. So here's the example of the Schnapps and Lights game, the very stupid one where you just have 5 cards and you want to play the cards in the right order so that you get to more than 22 as quickly as possible. That's all we have. And basically we have those 5 cards. So our 5 options that we have is playing the first card, playing the second card, playing the third card. But now, humans know that some of these cards are better than others. Yeah? So we have the clear understanding of the domain, we have the information that choosing a high value card first will bring us earlier to a goal state. Yeah? So if we would now, instead of looking at those 5 states that we can get to in some ordered way, then we could improve the search significantly. And basically what we can do now here is the value V that we would reach after a certain action, namely playing the card, the ace here, would give us some function, some value over the state, which says that this one is better than this one, because this one only has a value 2, and this one has a value 11. Yeah. So humans would play here clearly one of the cards which give us a higher value of V. Yeah. And this is basically what we're looking into today. How can we sort of formalize this knowledge and use it in the search space as relevant information to make the search far faster, so that we can get to the goal faster. And in the Schnapsen, as I just already told you, we would try to understand which of those 5 states is better than the others, and then try to evaluate the best one first. So what you do here, you take the order of exploration into account, and in technical terms, this means that we are going to order the fringe by some utility value. Yeah? And if we now think of the pyramid of the things that we're going to see in this course in terms of decision making, then it's first about finding systematically all the possible solutions, but now it's also takes some information into account, some heuristic values. Tomorrow, I'm going to show you how this will work if we have an opponent, and if we play games that are more interesting than our Schnapsen Light, but that really like chess or Go or the real Schnapsen, what kind of algorithmic search you can apply here. Today we only have one player, single game player, informed algorithms, and the algorithm is in principle exactly the same. It's the same algorithm that we saw before. So you have the tree search algorithm, you insert something into your fringe, you take out the first node from the fringe, and then you expand the nodes and add them again to the fringe, the successor nodes. Yeah? But now, this is the point where we say, why just put them at the end, and why not have an ordered list? And the ordering is based on some kind of human intuition that we call heuristics. So that's the notion of best first search. So we had seen the breadth first search where we just had a queue, and the depth first search where we had a stack. And now we have an ordered queue, a sorted queue in some decreasing order of desirability. So we take the one that is the most, so it must be in decreasing order. So we start with the most desirable solution, the one where we have the most trust that it will be close to the solution, and then we apply the algorithm in exactly the same way. And then there are some special types of these algorithms, and that's the greedy search algorithm, the hill climbing search A, and the famous AI algorithm A star. And this is the goal for today, to guide you through the notion of heuristics, to understand well what the heuristic means, and then look at these different types of algorithms and how they work. And that's basically also what will be 20-25% of the exam at the end, that you have to be able to apply all these algorithms on some simple examples, and that we're going to practice here as well. So, as I said, I have these evaluation functions, and I have the values of the cards that have been played. So if I play an ace, then I have the value of a state of 11, and if I play then a queen, then the value becomes 14. So I can have an estimation of the quality of a state just by the number of points that I have already achieved. Yeah, and that is a rule of thumb that could tell me that, okay, playing the highest card first to get the highest sum of values is a good choice, and I want to explore the next state from this one, so I put it at the top of the queue as the first node to evaluate. But it's not it's not a true value. It doesn't tell me exactly how good it is. It remains an estimation, because I could come up with slightly more complicated games where this simple guess doesn't work anymore. And I will show this example at the very end of the lecture. So these heuristics, they are always rules of thumbs, simplification, or even educated guesses that limit the search solution, because you hopefully don't have to evaluate all the ones that are not interesting. But it limits to the ones that you consider the most interesting possible first moves in your search. And heuristics are usually abbreviated with H. So a certain node in my search tree gets a certain value, and it's usually called the estimate cost of the cheapest path from the node to the goal, which means that your heuristic function should assign the value 0 to the node, which is the goal. Yeah? So that's one of the ideas that you have in one of those heuristic functions. Heuristics are really nothing more than educated guessing. Because in some instances we could calculate the perfect heuristics, as I might call it, but that is usually so expensive to calculate that I don't need heuristics anymore. I would use my search algorithm in order to calculate the heuristics. So the heuristics is really has to be very expensive, cheap to calculate, as opposed to the real knowledge that you might have, which is very expensive and often not even available. So remember that we have shown that you can, in principle, for the Schnapsenlight and other these games, you can look at the whole search tree, the whole full state space, but it might take you exponentially many nodes to look at, and even exponentially much space to store on memory. So that doesn't work. And that's why we need those cheap to calculate estimated guesses for telling us which of the nodes is the best one to explore next. And as I say here, they can be completely wrong. Yeah, it might be the case that these heuristics do not work. And I will show you an example of one of those heuristics that we can all see that it doesn't work and that it doesn't make sense. But let's start with some of the heuristics that make sense. And let's see how much sense they make. So we all know those puzzles where you can move one of the stones to another position, and the goal is to get them in one specific state. And in this case, the specific ordering of stones we want is that the 1 is in the top left corner, and then it's clockwise. So it would be 1, 2, 3, 4, 5, 6, 7, 8, and then the one in the middle is empty. Yeah? And here's an example for one possible heuristics, namely the number of incorrectly placed tiles heuristics. Yeah? So that might make sense that you say, I can now move the empty field, or you can move 1 or 7 in one direction. And what I'm interested in is the one which sort of reduces the number of incorrectly placed tiles. Whether that is a good strategy on the long term is a different question, but it's a valid strategy to try to order your next states. So in this case, let's count the number of misplaced tiles here. So this one is incorrect. It should be a 1, 1, 2. These are correct. This one is incorrect. Should be 3. This one is incorrect. 4, 5. Yeah? Or it's these 3 that are counted. Sorry, the empty one isn't counted. This one is incorrect, and this one is also incorrect. So it's 5 that are incorrect. And then the idea is, let's now look what are the possible next states that I could reach, that I could get to. I could move the 1 down. Yes, see that? And then I would still have how many misplaced tiles? 5. What would happen if I move the 7 to the left, which is the other option? I've got 1 more. I get 1 more. Yeah. So using this heuristics would tell me that I have to follow this one first. And then I have the choice, move the 5 to the left, which would decrease my heuristic value again, because the 5 is now correct and would not be correct anymore. So that one would not be good. But if I would move the 6 down, then this one would be correct. And that would be then a good heuristics that shows me, okay, I first move this one down here, then I move this one down here, then the next value will tell me that I need to move the 8 down, I guess, and so forth. And we can do that systematically, and probably if we use this heuristics on this example, we'll get to the goal pretty fast. So that's one heuristic that helps us in the search. So here's another one. And that's one which is very often used in anything where a distance is has to be calculated, physical distance, and that's the so-called Manhattan distance. And everybody who has been in Manhattan knows why this is called the Manhattan distance. If you want to get from some place in Manhattan to another one, you have to travel by blocks. So if the closest, the best way, the fastest way, unless you take Broadway, is to go one to the right and then x to the or n to the right and y to the up. And that is basically the distance of the tiles from the goal position in terms of movements if there were no other stones. Yeah. So let's see how that works on this example. One needs to be up here, so that's one movement. Two needs to be here, so that's another one. So we are at 2. 8 should be here, I think. So it would be 1, 2. So we have 4. 6 needs to be here, and 7 needs to be here, and that's 2 more, so we have 6. Is that clear? Yeah? So just count the number of moves you would do with the individual tiles. And now we could do the same exercise. If now we would move 1 down, the value would increase by 1, it becomes 7, because now the 1 would also have to be 2 up. And if we would use this one, I think the value would go down. So we would follow exactly the same strategy, and it would probably get us to the solution in exactly the same time. So there's one more, and that's the number of direct switches that would work, that would get a tile to the right position. So, and the value is 0 because we cannot switch any 2 objects such that both of them are at the right position. So then this heuristics, which also might make sense in some applications, in this one it does not. Yeah. So we see here already that there's quite some understanding of the game needed, even if it's such a simple game. This is going to be something that is really a very important part of AI, because the perfect solution for these problems that we deal with will never be able to be found. And then the question is, how can we find them? And a lot of that is based on the notion of heuristics. In whatever problem and whatever branch of AI you deal with, it's very often that you try to integrate these kind of rule of thumbs that come from some kind of human knowledge into your reasoning processes. So then, as you've already seen, there are different heuristics for every problem, and some of them will be completely independent of each other. Others might be dependent on each other. So we could, for example, have one where the value, if this is the perfect, the H star is the perfect heuristics, the 0 value is the lowest value, that the one that is closer to the perfect value is, and if it is true for all the nodes n, then we say that H2 is more informed than H1. And we have the perfect heuristics, which is always predicts the true evaluation value, and we have the trivial heuristics that doesn't do anything. And it can be shown that if you have heuristics that's more informed, you will have to with the I'm now doubting. I believe it's the other way around. So if you have a better heuristics, so if F2 is better than F1, then you have to search fewer nodes. Yeah. Sorry, I think this is incorrect what's here. But H1 is often more expensive. F2 is often more expensive to calculate. that one is correct. Yeah. So there is a kind of trade-off that we want to find the best heuristics, so the one that is as close as the true predictive value. And we often can calculate it, but it takes a long time to calculate it. And that's something that for every different problem you have to empirically try to understand, or analytically, but also very often empirically, to understand which of the heuristics works better on my specific problem. So here's an example for the travel example I showed last week for a completely meaningless and stupid heuristics, namely the length of name heuristics. And as we all know, if you want to travel from a town A to a town B, it is completely independent of the names these cities have. So you can very easily come up with wrong heuristics, and they will also guide you in completely wrong directions of the search tree. So let us now look at more interesting and more realistic heuristics and see how they can guide us and help us with the search process. And one of them is the so-called SLD, the what is the word again? Straight line distance, exactly, thank you. The B-line distance is also called the straight line distance. And so the straight E, I think. And by definition, is it an A or an R? Anyway, I'm a bit dyslexic, so that is allowed. So it's clear that if you want to travel between 2 points, you can choose whatever way you want. You could have you could also look at the Manhattan distance. If you have blocks, then it would be always in 2 directions. But there's also the one, which is the distance that the bee would fly, namely the straightest line between 2 points. And we will later see that this is a very good example because by definition it has a very favorable property that we're going to exploit in the definition of this A-star algorithm. Yeah? So what you very often have if you want to travel from one town to another, that you are given this straight line distance, which is the shortest distance if you were to fly, for example, but that doesn't take into account that you might have to travel a detour via another city, or so these 2 things are very often given separately. So here we have, for example, the straight line distance between all the cities from Bucharest, because remember the task that we were trying to solve here is to get from one of the places in Romania to Bucharest. And here comes always the question, are there any Romanian people in the room? That is very good news, because pronouncing these names is always a challenge. So we're going to look into this task of solving the problem of finding the shortest path traveling from Arad to Bucharest in a minute. But first I want to have a very quick look into the heuristics that we could apply for Schnapps and Light. So I have already told you one idea, and that is the idea to take the sum of the cards that you have already achieved as your measurement assessment. So which heuristics could we apply using this value or using other ideas or other values? You have any ideas? So first, let's use this value V. There are 2 different ways we could use it. We could have the highest value as a heuristics, but we could also have the lowest value of the heuristics. Lowest value would obviously not be very interesting if we want to achieve to get to the 22 value as quickly as possible. But if you would, for example, have the goal of the game that takes as long as possible, so how many moves can I maximally take before I get to 22, then suddenly your strategy would become start with the jacks, and then the queens, and then the kings, because then you extend the game as long as possible. So different heuristics might work for different games and for different problems. There could also be other things. So trump cards have other values than non-trump cards. We don't have trumps here in this very simple version, but that could be easily something you want to take into account. You could start with the spades, and all this depends on, in principle, the definition of the goal state. So now I have a very simple variant of the Schnapsen Light game. So we can't play simply all the cards we want, but we always have to play the card in the same color than the one I've played before, if I have one. Yeah? So it would mean that if I have, if I play this ace, I would have to play these two afterwards. But if I would play this one, I could play whatever I wanted. Yeah? So I'm bound by the colors until they are gone, and then I can play whatever I want. Okay, so now I might have to use a different strategy, different heuristics. Yeah? So what kind of heuristics would you now look into? Or combinations of heuristics?
Maybe they hide this card, you can get which owner has the less card in the same color, so you can switch to the color.
Yes, so I think that would be a very useful suggestion. So you could, for example, multiply the number of colors, cards in one color times the maximum. So that would be 11 times 3 or something, or divided by 3, normalize it. You would normalize it by 3. And then this one would be 11 normalized by 1, so you would have this one first. Yeah? So I think that's a very good idea to combine those two, and you can combine them, as I just showed you, you can combine those two elements of the highest cards and the one that has the fewest cards in the same color. You can combine that into one heuristic. Just normalize the highest card by the number of cards in this color. Yeah, and then we have just one new heuristic value that we could use in order to play the game. And I think, honestly, that this is a very good heuristic for winning this variant of Schnapsen. And the other one will not work. So if you apply the heuristics that we had before, it will not work. Because then you will probably start with this one, and you will have to play all these low cards afterwards before you're allowed to get to the ace. So you need 4 steps before you get to the 22. Yeah, and obviously tomorrow we are moving from this trivial Schnapsen Light version to the proper Schnapsen, where you have an opponent. But then the idea of looking at those heuristics according to the values of your cards and the values of the cards that have already been played on the table and so forth, that will still play a very important role. Okay. So here's the original one, the highest card first. And then afterwards, the card from the most frequent color or the card from the least frequent color. And that's the one that we just formalized here. Yeah, so this is the combination of these, the first and the third. So now we have this notion of heuristics, and we can now measure in practice the quality of these heuristics. There is a formal way of formalizing this is by what's called the effective branching factor. Basically, the effective branching factor is a theoretical notion that if you had a uniform tree, then what would be the branching factor of this tree in order to produce a certain number of nodes. And this is a very useful measure because it's easy to calculate. If you have your search tree, you just count the number of nodes that you have to create it, and then you can describe your tree as if it was a uniform tree, and this value of B1 then gives you the quality, because you want to have your tree as small as possible. And here's an example for some random problems with a solution length between 2 and 24, where I'm not sure whether you can read it. There are two heuristics, H1 and H2, and there is iterative depth search as a comparison. And so if you use this uninformed search, you basically can go up to depth of 12, and it takes already a lot of nodes that you have to calculate through. And if you go deeper, if you can go deeper, then your tree search algorithm just explodes calculation-wise. Yeah. But if you apply a good heuristics, and in this case we have two heuristics, H1 and H2, then H star, the algorithm that I show in a minute, is far better, and you can really get to twice as deep in the tree because you only have to explore part of the tree. The interesting thing now is that, of course, we can also see that the number of nodes that we have to explore, given the better heuristics, is far smaller. But there's also this notion of effective branching factor, where you basically show that in iterative depth search, you have a certain uniform branching factor that is around 3. And here the number is smaller. And if you get towards the smaller, the better. So the best one would be 1, because then it would be just linear search. So this describes how you control your breadth of the tree, because remember last time I explained that the real cost of a search is the breadth search. If you create a new level, then you add a new level of exponentially many nodes that you have to look into. And if that is only a factor 1.2, then you can, of course, effectively search much deeper than you could before. And here you can imagine that this kind of things were something that were really crucial when, in the 90s, they built the chess game algorithm, because you want to look into the future of a chess game for 10 moves, 20 moves, and so forth. And then it really becomes crucial that your effective branching factor is relatively small. Otherwise, you can't look forward into the future as much as you would like to. In 4 weeks, I guess, we also look into the question of how you can learn these heuristics. Because basically, what you probably have understood from the introduction lecture by Mark about machine learning, one of the tasks is that if you have a database where you have specific values attached to a certain number of features, then you can simply train a regression algorithm that predicts this value. And this is exactly what we want here with the heuristic value. We just want to assign to a state a heuristic value. And why not learn that when we use all these features that we have as our training input? So the idea is we model a game in a features space. So a number of things, for example, how many high cards do I have? How distributed are the cards? How many cards does my opponents have already won? How many points, and so forth. So you make as many of those features explicit turn them into numbers. And then given a certain card deck that you have your machine, your algorithms play hundreds of thousands of games, for example, against itself. And then you check for a certain state, whether it wins or not. And the higher the probability for this state to win is, the better the state is. And that is something you can learn on the basis of games that your engine plays. Yeah.
Table says like the values for H2 are smaller than the values of H1.
Yeah, I think you're right. I will have to check that. I think that the H1 and H2 indices are somehow switched here. So I'll no, you're completely right. But that was on the slide before. It was the same problem. I think it was the wrong way around, and I need to fix that. I need to check that. I will tell you. H2 is more informed. This one is more informed. And if it's more informed, then it should be better for search. And what now exactly this notion of domination, what the definition of it is, I don't know out of the top of my head. So it could be that this is weird, but it could be that it's wrong. Yeah? So you had a question there in the middle as well? Yeah. I will have to look it up. I will get back to you on that. Yeah, I'm sorry, I can't tell this now. I do not think it makes sense. No, let's not lose time on that. I have to look it up, and I will tell you tomorrow. So this is something I wanted to point already to the future. Would you mind stopping that? We're not at sort of 5th grade. So this is something you're going to have in the second assignment. Basically, this is what we're going to do. We transform the game into features, the states of the game into features, and then we have our game engine that you all have now up and running and have thousands of games played machine against machine. And you just check out how good is how important is a certain feature to predict whether a state will win or not. And you use that one in a regression algorithm to determine the value of your heuristics, and that will then be determine the next choice of node. Okay, so I think it's now time. This clock is wrong, but I think it's time for a break. So I would suggest if we could start at 5 o'clock, and then I will get into the algorithms that are based on these heuristics. Okay.